The hell? Okay. No idea how this is going to look like. Yeah, so I forgot to recharge the iPad, so I have to. Anyway, who cares? Okay, so all right, 5.1 induction. It's going to be fairly short today. I want to finish 5.1. So, and I've got like 3 examples that I want to do, but they are a bit more involved than what we did yesterday. And I'm not sure I want to start 5.2 right now because I'll just end up stopping right in the middle, and then it'll take a whole week before we start over again. So it's sort of not worth it. Okay. Okay, so let me restate induction. The more general version that we saw. Um, Principle of induction. Here we go. So we take some, I think this is maybe not quite phrased this way in the book, but I'm sure, I mean, this is the difference is so slight that I'm sure you won't have any problem with this. So I take any integer, could be negative, 0 or positive, and suppose the set S satisfies the following conditions. Yeah. First of all, B is an S. And second, for any integer greater or equal to B, if n is in S, then n plus 1 is in S. Then S contains every integer. I didn't state it. I realize now I didn't state it in this form yesterday. I'll just restate it with the property version. So S contains every integer n greater or equal to B. Okay, it could be bigger, but it's not. That's irrelevant for us. So it doesn't matter. So if it contains B, and whenever it contains an integer which is at least B, and then it contains the next one, then it contains everything starting at B. Okay. So this is the form as a set. If you want to see it as a property, so let's say property, suppose property P satisfies the following. First of all, P of B is true. And 2, for any n greater or equal to B, if P of n is true, then P of n plus 1 is true. Then the conclusion is that P of n is true for all n greater or equal to B. Okay, which is the same, it's exactly the same thing. Whether I'm using the sets or the properties, it's the same thing. Okay. All right. So what I want to do now is to do 3 more examples, which are a bit more involved. Okay. Yeah, I forgot to say that chapter 5 deals with induction. In 5.2 and 5.3, we're going to see variants of the principle of induction. In 5.2, it's called strong induction, and which is a really bad name because it's actually not stronger than induction. It's perfectly equivalent. But in certain cases, this variant, which is a name, a word which is in the air, right? So this variant will be useful in certain very specific instances. And the third version, so I think it's 5.3, um, uh, is also totally equivalent. It's the well ordering principle, which is an equivalent way of stating induction, but turns out that looks even simpler. But we'll see that in, not next week, but the week after. Okay, so here are our three other examples. So here's our first example for today. This is something we saw in chapter 2, and I vaguely proved it using binary strings, which is a totally valid proof, but at the time I didn't do it, in all the proper details. So here's a first formal proof of this fact that you know that if a set X has n elements, then its power set has 2 to the n elements. Okay, and this is for any n greater or equal to 0. Now, recall that P of X, what is that? P of X is the power set of X. This is the set of all subsets of X, right? So for example, if X is 1, 2, 3, then the power set of X consists of the empty set, the one element sets 1, 2, 3, the two element sets 1, 2, 1, 3, 2, 3, and the whole set itself 1, 2, 3. And you see this set X has 3 elements, and the power set has 2 power 3, 8 elements. So at least we see that this is true for n equals to 3. Okay, so this is a very, very nice little proof. Okay, before I show you the proof, I want to illustrate the basic principle behind the proof before I jump into the actual proof by induction. Okay, so this is to illustrate the key idea in the proof. So it's a proof by induction, but as I said, when you have a proof by induction, at some point you have to use the induction hypothesis to prove, if you suppose P of n is true for a certain n, then you want to show P of n plus 1. Anything goes. Depending on what you're trying to prove, you might have to use all sorts of stuff. So this is that idea here that I want to illustrate. So let's consider this set X again, right? 1, 2, 3, and I want to look at this. So we have these subsets, right, which are listed over here. That's how convenient. I didn't prepare this, and it works out well. So let's just consider the element 3 as a special element that I'm going to isolate like that. Okay, and I'm going to look at there are 2 kinds of subsets, right? So 2 kinds of subsets of X, those containing 3, and those that don't. Very deep, right? So there are subsets that contain 3, and there are subsets that do not contain 3. Okay, so let's look at those over here. right? So these are the subsets that contain 3. And then you have those that do not. Now let's compare these two kinds of sets, and you will see you'll see a pattern, and that's the whole idea behind our proof. Okay, so what's the pattern here? Okay, so look at those that contain 3. There's 3, 1, 3, 2, 3, 1, 2, 3. Yeah, and those that don't contain 3, let's use a different color, say blue. These are those that do not contain 3. And I don't know if you can see, but first of all, there's the same number of them. And there's a nice reason for this, right? So if you consider a subset that contains 3, okay? And remove 3, obviously you get back a subset that does not contain 3. Okay, but you see that if you do that, you will get every single subset that does not contain 3, right? So by removing 3, I should say consider all subsets. That's what I want to say. By removing 3, you will obtain all possible subsets that do not contain 3. Right? I mean, just looking at the examples, the example here, you see this is true, but the idea is simple, right? So if you take the set 1, 2, 3 like that, right? Take any subset that contains 3. How is it built? It's built from a subset of this part, and you add 3, right? They're all of this form. So that's exactly what you see over here, right? So 3, 1, 3, 2, 3, 1, 2, 3, right? So it's just basically you took the empty set 1, 2, and 1, 2, and you added 3 to all of them. That's how you get all the subsets containing 3, okay? And that is basically a general principle, right? We're going to use in our proof. Okay, so hopefully you see what I just did here. Okay, so here's our proof now of the general statement. So the property of the integer n is this: if x has n elements, then the power set of x has 2 power n elements. I want to show that this is true for every n greater or equal to 0. Okay, so we're going to use induction. So the induction basis, I want to show p of 0. What is p of 0? If x has no elements, that means x is the empty set. What is then the power set of x? What are the possible subsets of the empty set? There is only one. It is the empty set itself. And so p of x has one element, which is 2 power 0, okay, which works. Okay, so p of 0 is true. Now I want to show that if p of n is true for some n, then p of n plus 1 is true. So suppose p of n is true. And again, I mean not for all n, but for some fixed n. Okay, to show p of n plus 1. So what is p of n plus 1? It is that if a set has n plus 1 elements, then its power set has 2 power n plus 1 elements. That's what I want to show. Okay? All right. So let's see. So I have x, which has n+1 elements. Okay. I want to use that little trick that I showed you for 3. So I'm going to pick an element in X. It doesn't matter which one. Notice that X cannot be empty. This is important because it has n here is at least 0, and we have n+1 elements. So there's at least one element. So choose some element A in X. Okay, so, and I want to count the number of subsets. So what I'm going to do is I'm going to count those that contain A and those that do not contain A. So there are 2 kinds of subsets of X, those containing A, those not containing A, right? Okay, so let's see. Let's start by counting those that do not contain A. Okay, so let Y be the set X where I've removed the element A. Okay, so this is the whole set X, but I remove A. How many elements does this set have? It has n elements. So by induction hypothesis, the number of subsets of Y, so the number of subsets of Y, and what is that? That's the number of subsets of X that do not contain A, right? That's the number, I'm writing a lot of stuff here. Number of subsets of X not containing A is 2 power n, right? That's the induction hypothesis. So I've removed an element from X. I look at all the subsets of X that do not contain this A. So these are exactly the subsets of Y, which has n elements. So there are 2 power n such subsets. Now I want to count those that contain A. So think of that 3, the trick with 3. So how do you build a subset of X that contains A? You take a subset without A and you add A, and it's a bijection. There's exactly the same number. Okay, so the number of subsets of X containing A is the same, since every subset of X with A is equal to a subset without a union A. Sorry, I was just really okay. So it's shorthand. Okay, but you saw the previous example. Hopefully you believe this. Okay, so if you take any subset which contains A, you just remove the A, you get a subset without A, and there's exactly one for each, right? So that's the same number. So total number of subsets. So with A, 2 power n. Without A, 2 power n. So total 2 power n plus 2 power n, which is 2 times 2 power n, which is 2 to the power n plus 1. Hopefully that makes sense.
Yeah.
Yeah? All right. Good. Okay. So power set contains 2 power n elements, and this is true for any number of elements 0 and up. Okay? So that's my first example. So you see we had to work, I mean, the induction part is always the same, but there might be some special argument necessary inside the proof. Okay, so let's, okay. Let's take a look at our second example. This is harder. This one is, it's really cute, but it's the kind of problem you have to spend time with. If you're lucky, it goes really fast. If you're unlucky, nothing happens. So here it is. This is difficult. This is a tough one. So we are asked to prove that 57 divides 7 power n plus 2 plus 8 power 2n plus 1 for every n greater or equal to 0 and an integer.
Sorry, what's the first thing? Prove that what divides 7?
57.
Oh, okay, sorry, thank you.
Okay. I think a couple of years ago, a student came up with a proof without induction. I think. I don't remember it. So, I mean, when all else fails, for sure, if I asked something like that on a test, I wouldn't force you to use induction. You know, whatever you can do, just. But that would be a tough one. If, of course, if you've never seen it before or anything like it before, then it's a very difficult problem. Okay. If you've seen one before, then that changes the whole perspective, obviously. But let's see. Okay, let's take a look at this thing. So I'm going to do a proof by induction. Big surprise. Okay, so what's the statement? The statement is that 57 divides this for any n greater or equal to 0. So let's see, what is p of 0? It should be that 57 divides 7 squared plus 8 power 1. That's 49 plus 8, which is 57, and that was easy. Yes. So that's not the hard part, obviously. Okay, so now suppose p of n is true. So that means 57 divides 7 to the power n plus 2 plus 8 to the 2n plus 1. Prove p of n plus 1. What is that? 57 should divide 7 to the n plus 3, right? Plus, and be careful with that, 8 to the 2 times n plus 1 plus 1. So it's not 2n plus 2, but it's 2n plus 3, right? Be very careful with that. Okay, so that's what we need to do now. Okay, so look, obviously, like I said, this is really important. I mean, you might be able to find a proof which is direct. It could happen while you're messing around like that. You might happen on a direct proof. But if you are trying to do a proof by induction and you don't use the induction hypothesis, you're in big trouble. Okay, chances are you made a mistake. Okay, so you have to use the fact that 57 divides 7 to the power n plus 2 plus 8 to the power 2n plus 1. So if you are going to use that, then obviously, I mean, you're looking at this here. We have to get, so strategy. So we need to get 7 to the power n plus 2 plus 8 to the 2n plus 1 involved somehow, right? That's for sure. But you see, things are added together and it's not super clear how you can actually do this, okay? So this is the part where, must fool around with expression and if we're lucky, something good will happen. I mean, that's basically it, right? So I'm not going to, so there are a couple of things. There's a couple of ways of actually making this work, maybe more, but I'm going to show you one of them. Okay. So here is one. Okay. So I've got 7 to the power n plus 3 plus 8 to the power 2n plus 3, right? So this is what we're looking at. And I'm hoping to get 7 to the n plus 2 plus 8 to the 2n plus 1 involved somehow. So here's my first step, which doesn't appear to be so good, but let's see. So I'm going to write this like that. 7 to the n plus 2 times 7, which is maybe what many of you would have done, right? So 8 to the 2n plus 1 times 8 squared. That's for sure, this is true, okay? And I sort of have what I want involved, but not in the right way, right? I want to show that 57 divides this thing, and I know that 7 divides that sum, but it's not, it doesn't appear as a factor, right? So what can I do with this? Well, here's a little, I mean, this just, sorry. So notice this. And in fact, I mean, I still haven't, I mean, there might be a very general pattern here, but I don't see it yet. Haven't seen it. But notice this. So 8 squared, that's 64, right? 64 is 57 plus 7, okay? So let's rewrite that 64 there as 57 plus 7. Let's just do that, okay? And again, if you're asking me, where does this come from? It's just like, you mess around and it happens, okay? So let's see what happens. We've got 7 to the n plus 2 times 7 plus 8 to the 2n plus 1 times 57 plus 7. And at this point, if I gave that to you in this form, I would think from here on in, it's an easy problem. It's a fairly easy problem. I want to show, so again, I want to show that 57 divides this, knowing that 57 divides 7 to the n plus 2 plus 8 to the 2n plus 1. Okay, so if you look at this thing, you'll see that you can rewrite it in the right way, because this is 7 to the n plus 2 times 7 plus 8 to the 2n plus 1 times 57 plus 8 to the 2n plus 1 times 7, right? I'll just reorder them. So this is 7 to the n plus 2 times 7 plus 8 to the 2n plus 1 times 7 plus 8 to the 2n plus 1 times 57. I just flip those two terms, right? And hopefully you see now that we win, right? Because this is 7 to the n plus 2 plus 8 to the 2n plus 1 times 7. We finally have this part in the form we want, and the second term is a multiple of 57, so that's great. 8 to the 2n plus 1 times 57. And we're good, right? So induction hypothesis. So 57 divides this. That's the induction hypothesis, right? 57 divides this. This is obvious. And if 57 divides those two, then their sum. And so 57 divides the whole thing. Now we're done. Okay. Other than how the hell do we get there? Do you see the steps, right? Once I've got that really nifty little trick of writing 64 as 57 plus 7, rearranging. Hopefully everybody sees that this works out. Is that good?
Yep.
All right.
Yep.
Okay, so again, how do you find, I mean, that's the key point, right? That's intuition, that's art, that's luck. And if you don't see it, you just die with your problem. I mean, but I think it's the kind of thing that you mess around, and this is not the only way to do it. Actually, you can, there's a slightly different way of doing this, but it's similar. It all comes out to the same thing. But anyway, okay, so that's okay. Last example, which is a really cool one. Okay, example 3. And the examples we're going to do in the next 2 sections will look more like the one I'm going to do now, which has nothing to do with numbers, basically. So this is something called the odd pi fight. So here's the setup. So it's a game, okay? So we have an odd number of people, and each has a pi. And they all stand, this is important, they all stand at mutually distinct distances. Okay, so if you measure the distance, between any 2 of these people, you never get the same value. Okay, right, so you measure these distances like that. They're all different. A, B, C, all different. Okay, that's what it means. And here's what happens at some point. Somebody blows a whistle and everybody throws their pi in the face of the person who is closest. Okay, so everyone throws their pi at the closest person. And you don't put your pi in your own face, right? Other than themselves. So show there exists a survivor. In other words, there exists someone who doesn't get fix your muffler, who doesn't get a pi in the face. Okay, so we have an odd number of people standing at mutually distinct distances. Somebody blows a whistle, everybody throws their pi at the closest person. And you see there's only one such person, right? Because the distances are all different. There can't be 2 people which are the same distance from me. There is a closest one. I throw my pie at this person. So in any possible instance of this game, there will be someone who will not get a pie in the face. That's the job we have, is to show that this is the case. Okay, so we have to set this up properly, and we're going to use induction to show this. So I need to have a statement for every n. Now, if your n's are odd, this is not good, right? Because induction works for consecutive integers. So we're going to, so this is the first important thing. So what is P of n? This will be the statement in every instance of the game with, I want an odd number of people, so I will put 2 plus 1. People would throw pies at each other in pairs, so there's a survivor. It's not the case, and it says domino effect, so it's also a survivor. Not quite. So here is, but that's a good point, but that's not what happens actually. Let me just make the statement and then we can discuss a little bit what this might look like. But you might be the closest person to me, but I might not be the closest person to you. You see that?
Maybe you could illustrate the example with the
Yeah.
3 you just put at the top with
Well,
the ABC.
yeah, so here, yeah, but okay, let me finish the P of n, and then I'll show you, okay? So in every instance of the game with 2n plus 1 people, there exists a survivor. Okay, so this will be n greater or equal to 0. Sorry, I want to start at 0, right? Okay. Some discussion. Okay, so let's take a look at it's annoying. Maybe this and maybe that. Okay, let's say these are the 5 people. Actually, you know, I'd have to parse your comment, but maybe that's the proof. Maybe you just basically, but either you have the proof right there, or I didn't. I don't know. Okay, let's just, okay. So, but people would throw pies at each other in pairs. That's not quite true, because, okay, so this person will be hitting this person. This one will be hitting this person. That, yes, that's true. This person will throw at this person. I should have put this one further out. This person will hit this person and this one, like that. Okay. But you see that it's not in pairs. I mean, the 2 closest ones, yes, the one, and that will play a role in the proof, absolutely. But yeah, no, maybe, not sure. For sure, the 2 closest, and that's part of the proof, that the 2 closest ones will throw their pies at each other, for sure, right? Maybe, I don't know. But what's your conclusion? That it's a domino chain reaction. One guy throws another that's close, the other guy throws it closer. But it might be more complicated. Maybe I have, let's see. Let's put somebody here. So this goes like that. Maybe we can have somebody here. That's not interesting. Somebody here goes here. I've got 8 people. That's not very good. Yeah. I don't know. I don't know if I'm answering your question or if you have a question. I'm not sure what you mean by domino chain reaction and what the conclusion of that is. Yeah, okay, yes. Yeah. So yeah, so this is tricky, right? Because sometimes we have this intuition, which that's what I see from what you're writing, is you have possibly the right intuition, but you have to be able to write it down properly, which is what I'm trying to do with my PhD student right now. And no, I shouldn't get into that. But okay, writing proofs is important if you want to communicate your ideas. Getting the intuition is also good, but you have to be able to do both. Okay. So my guess is that you sort of possibly have a good intuition. Okay, but let's try to write this up properly. Okay, so let's see. So hint, we're going to use induction. Okay, maybe there's a proof without induction. I don't know, but it looks unlikely. I mean, maybe, I don't know. Okay, so that was that was sort of discussion. I don't know. Okay, so here's the proof by induction. And there's something in it which is really important that I want to discuss, which is really, really very important.
I don't know if it's just me, but the screen is not updating and you seem like you're writing.
Yeah, from
Oh.
Carlos. I
Yeah,
also
me
thought
neither.
that was
Yeah,
wrong.
me neither.
Okay, yes. Wow. Okay. I probably have enough battery to switch this around. So let's go back to our normal setup. Let's stop this share. Let's share this.
It's all good.
All right. This is good. Okay, excellent. Okay, so let's prove our statement by induction. So what is P of 0? So the player is alone. There's a single player, so obviously this player will not get a pi. So this is obvious. Okay. So now suppose P of n is true, which means what? It means in any instance of the game with 2n+1 players has a survivor. Okay, I want to show P of n+1, any instance of the game with 2n+3 players has a survivor. Okay, and again, we want to use our induction hypothesis at some point, or else something goes wrong. Okay. Again, I mean, if you're doing a proof, I mean, if you don't use the induction hypothesis, that might happen, that you find a proof which is not by induction, but then you should erase everything and just, so here's a direct proof if that's what you're looking for. Okay, all right. So let's take a look at what Raphael was saying, because certainly there's something there, which is the following. there are two players. So the distances are all different. So there are two players which are closest to one another, right? The distance between these two is the smallest. So there exist two players closest to each other, because all the distances are different, so you can list them. So there's a smallest one, right? Since all distances are distinct. So this is where this is used. It's important. Okay. So these two players could be as simple as the point that is the furthest from the closest point is the survivor. The furthest from the closest point. I'm not sure what that is. Oh, you mean from? Not sure. Nope. Nope. You could have another pair that hit each other. They're like super far, like in my example here, right? So you see yeah. Let me show the proof. So here is the person not getting hit is here. So, okay. So there exist two players which are closest to each other. Okay. They will throw their pies at each other. So they throw their pies at each other. Let's look at the remaining 2n+1 players. That seems like a reasonable thing to do, right? We want to use our induction hypothesis. So consider the remaining 2n+1 players. Here's the very, very, very dangerous trap. And I'm saying this as a professional mathematician because it happens. We all mess up. When you're using induction, you have to make absolutely 100% sure that you can apply your induction hypothesis. This is really important. Okay. So if we look at the remaining 2n+1 players, it's very tempting to say, there's a survivor because these players are throwing these pies. There are 2n+1 players. I apply the induction hypothesis. So there's a survivor and we win. There's something wrong with this argument, and very wrong. What is it?
One from the initial pair could be pied another time.
Yes, exactly. So that's the trouble. So the problem is that these 2n+1 players do not necessarily give you an instance of the game with 2n+1 players. If you have an instance of the game with 2n+1 players, they have to throw their pies at each other. They can't throw pies at outside, right? But this could happen. One of these 2n+1 players might throw a pie at those two closest players, right? Okay, so there are two cases, okay? So warning, be very careful with that. You don't want to go too fast. Okay, so there are two cases. Okay, case one. So these 2n+1 players throw their pies at each other. I mean, among themselves, okay? And so this is an instance of the game with 2n+1 players. So induction hypothesis you can use here for sure, right? So there exists a survivor and we're done. Okay, so if these 2n+1 players throw their pies at each other, then this is an instance of the smaller game and I can apply the induction hypothesis. So what's the other case? And this is where I think what you were talking, when you were talking about a domino effect, this is where it's, so you had, I think you had a really good intuition. Overall, you had a very good intuition. Case 2, it means some pi from those two n+1 players goes to those two first players. So some player from these two n+1 players throws its pi, her pi, his pi outside. So add the two closest players. Right, so we have these two players that hit each other. I have all the other guys here. And somebody throws their pi outside. So then I'm not allowed to use the induction hypothesis. It's just, there's no way to use it, okay? So you just forget about that. So, but then I think this domino effect you were talking about is this, right? So if a pi goes outside, there's not enough pies for everybody. So for sure, someone is not going to get hit by a pi, okay? So, but in this case, a pi goes out. So not enough pies for all two n+1 players. So there exists a survivor also. And that's the proof. Does that make sense?
Yep.
Yeah.
Yeah.
Okay. So the more general thing that I wanted to say is here is that it's very tempting when you see those two n+1 players, really tempting to just to jump on the induction hypothesis and to say, I'm done. You always have to check that all the conditions are satisfied. And you see here, they might not be. So there are two cases. There's the case where they are satisfied, you're all happy. Why does this not respond anymore? Okay. But then there's the case where you have a pi going out, but then you're fine. It's sort of almost easier in that sense, right? Okay, there's in the book, if you look, there's an example of a very famous bad proof by induction, where you prove that there are various versions of this, that everybody is Elvis, or everybody is on an island. But somehow the only time I tried to do that in class, everybody looked at me and said, what the hell are you doing? So I'm not going to do it. I refuse to do it. So you can read it. So, but please be careful. There are traps. And I think it's related to what we discussed yesterday very briefly when we said you have to start the M, you have to start at the value B. Right. So if you make a silly hypothesis where you start after, you might be able to show things that are very, very not true. Okay. So be careful with that. Okay. That's basically what I wanted to do today. So, which is 5.1 is done. It's a good place to stop. If you have questions on chapter 4, I am available. And Thursday I'll do problems. I'll do problems for the test, and yeah. So and then we'll get back to this after the test.
Perfect. Thank you.
All right.
Thank
Have a good day.
Thank you.
Thank you.
Cheers.
Have a nice
See
day.
you. Bye bye.
Bye, sir.
See you.